Let us continue our lectures. Till the previous class we talked more about the finite element modeling, and we have also seen some particular aspects related to geotechnical engineering, that is related to sliding along any preferential direction like through the interface elements, then modeling of semi-infinite soil media through our mapped infinite elements, and then we have also seen the gradual construction and then removal of soil excavation, and we have seen how to simulate that type of geotechnical aspects. And from this class onwards we will focus more on the soil behavior and its constitutive modeling, and then what are some aspects related to analysis with nonlinear response or plastic response and so on. Okay. And before we go into the analysis aspects, let us look at some observations on how the soil behaves, so that we can then we can think about modeling. Then of course towards the end I will also introduce the stress invariants. That is one of the most important aspect of any constitutive modeling, and this is what we see right from our undergraduate days on the soil behavior. We know that a dense sand or an over consolidated clay, when it is subjected to shear strain, it will have a nice peak, and then beyond that it will undergo some strain softening, and then at a very large strain the stress will remain constant, and that we call as the critical state. And in the case of loose sand or normally consolidated clays, the stress will go on increasing with strain, and then after a very large strain we might reach some asymptotic limit, and we see that the ultimate limit of both the dense and the loose sands is the same, and we call this type of behavior as a strain hardening behavior. And in the case of dense sands, this is our strain hardening behavior, and then we have the strain softening behavior, and the additional strength that we have between the critical state and then the peak stress, we say it is because of the interlocking effects. Then if you look at the volume change response, the loose sands will go on compressing, then at some stage they will reach a constant volume state, but they will undergo volume compression predominantly. Then in the case of dense sands, they might undergo some volume compression depending on the initial relative density, and then after some time the soil will expand in volume, and this expansion in volume under the shear strains we call it as dilation. That is a specific term that we have in the case of soil mechanics. Then at a very large shear strain we will reach a constant volume state, and that is related to the critical state. And so this is the basic difference between dense sand and a loose sand, and then we have to see how to model them through our constitutive models. And the reason for this is very simple. So if you look at the packing, the soil packing, and then the shape, whether they are rounded particles or spherical particles and then angular particles and so on. So if we have a uniform packing like this, uniform packing of soil particles, all spherical particles of uniform size, and this will have an initially very high void ratio, and then if you subject that to some shear strain, the particles tend to fill up the voids, and with the result that you will the soil will undergo volume compression. And the analogy for this we can look at by looking at these two serrated plates, let us say that initially the two plates are arranged like this with a very large spacing between them, and if you subject them to any shear strain, after some strain you will see that the upper plate will fill up the bottom plate and they will come together, and that is similar to our volume compression of the loose sands. So, we can say that this is analogy of the loose sand behavior. Initially there is a large gap between the two plates, and that is corresponding to our initially high void ratio. And then if we look at well graded soils or the sands with very good angular particles, there could be a lot of interlocking between the particles, and then you can and when you subject them to any shear, let me just so actually in the case of nicely arranged particles, there are predefined shear planes like this, and then the soil will deform under shear strain without much of volume change, or there could be some volume compression. But then here there is no single plane on which all the particles are very nicely arranged. So, if you have to develop any shear, then you have to deform or move the particles, some particles away from the shear plane, so that we can nicely form the failure, and that type of situation we can think of by these two interlocked plates. Let me just get back to my laser pointer. Okay. So, here we have two interlocked plates. If you subject them to some shear strain, the only way the shear strain will take place is when the two plates move away from each other. That is similar to our dilation of well graded or densely packed soils, and this expansion in volume or the moving away of the plates is happening against the applied normal pressure. So, the shear strain has to do some additional work to or the shear stress should do some additional work to cause the shear strain. Apart from the shear strain, it has to also act against the normal pressure. So, because of that the soil might have some additional strength, and in fact that is what we see in the form of this additional strength that you have beyond your critical stress, and this we call as the interlocking strength. And then what are the volume changes? See, let us think of our triaxial compression test, because that is the simplest stress state that we can imagine. Let us say that we have applied an axial strain increment of d epsilon zz, and the two lateral strains in the x and y directions could be written as minus mu times d epsilon zz, and the volumetric strain increment is the sum total of all the three normal strain increments. So, d epsilon v is d epsilon xx plus d epsilon yy plus d epsilon zz, and that is equal to 1 minus 2 mu times d epsilon zz. And so, our Poisson's ratio is less than 0.5. The theoretical range is from -1 to 0.5, but negative Poisson's ratio is impossible, because we see that if you elongate in one direction, the other direction there is compression, or if you compress in one direction, there is elongation in the other direction. And so, our Poisson's ratio is always positive, and it is less than 0.5. So, if the Poisson's ratio is less than 0.5, let us say 0.4, 1 minus 2 mu is 0.2 times d epsilon z. So, that means that our volumetric strain increment will have the same sign as the axial strain. So, if your axial strain is compressive, your volumetric strain is also compressive. So, we can say that all our elastic volume changes are only going to be compressive as long as you apply some compressive stresses. And on the soil particles, we cannot anyway directly apply any normal tensile strain. We can apply shear strain, but we cannot apply any tensile strain. We can apply compressive strain or compressive stresses. So, our dilation induced volume expansion we cannot model through any of our elastic equations, elastic or nonlinear elastic models, because our Poisson's ratio will not allow us, like 1 minus 2 mu d epsilon z is our volume strain, and at a very large strain at constant volume state, when d epsilon v tends to 0, this should tend to 0, and we see that the mu should tend towards 0.5 to keep the volume constant. That is, the further increments of the volume strain should be 0. So, our mu is 0.5 towards the critical state, and in fact, we do not write any equation like this. We write it as mu tangent, because the Poisson's ratio also keeps updating as we are applying strain. The Poisson's ratio might change along with the modulus values. And if you have an undrained response of soil, because that is that's associated with the 0 volume change, we can simulate the undrained behavior by setting the Poisson's ratio close to 0.5, maybe 0.49 or 0.499, and that is actually incompressible behavior. And this is one simple way of simulating the undrained soil response. See, we could have two friction angles. One is corresponding to peak in the direct in the shear test that we have performed on the dense sands. We have a very nice peak, and then the strain softening, and that peak stress, corresponding to that peak stress, we have the phi peak or the friction angle, the peak frictional strength. And at a constant volume stage, you will have your tau CV, and through that we can get phi CV, the friction angle at constant volume. And in the direct shear tests and simple shear tests, the tan psi is just simply the slope of that line, dy by dx. If x is the shear direction and y is the volume or vertical direction, tan psi is just simply dy by dx. And the phi peak is approximately equal to phi CV plus 0.8 psi or phi CV plus psi. So, actually this is from one of the classical papers on soil dilatancy that was published by Professor Bolton long time back, and there he has described the soil dilation and its relation to the gradation, and then the particle shape and so on. And in the Plaxis program, there is a thumb rule given that the dilation angle, if you have not measured from the laboratory tests, it could be taken as the phi minus 30, assuming that about 30 degrees we can think of as the starting point of any dense sand, and any angle beyond 30 degrees we can take it as a dilation angle. So, if your friction angle is 35 degrees, your dilation angle could be 5 degrees. And one point that we have to remember is the finite element programs will have lot of difficulty converging to a solution at very high peak value, shear strength values. Like if your phi is beyond about 40 degrees, if you try simulating any bearing capacity problem, you will see that the program will just simply fight to converge. You will see a lot of oscillations in the stress that you predict. So the dense sands exhibit very sharp peak, and its stress strain response will have a very nice strain hardening part and then a strain softening part, while the loose sands will have only a strain hardening part. The stress will go on increasing with the strain. Then at a very large shear strain, we might reach some asymptotic limit, and the dense sands may initially compress in volume, but undergo volume expansion under increasing shear strains. And then the loose sands, they will exhibit only volume compression under shear straining, and at a very large strain, both the dense and loose sands will exhibit the same strength at the critical state. And when we develop any constitutive model, we should be able to exactly replicate some or all of these features. We will see different types of constitutive models that can simulate this type of behavior. And the initial higher strength of dense sands is due to interlocking of the soil particles, either because of the gradation or because of the particle shape. And the volume expansion is called as the dilation, and it's due to the plastic straining. It is not during the elastic state or elastic straining, but during the plastic state. At critical state, our volume of the soil remains constant, and the Poisson's ratio is near to 0.5 at the critical state to represent our incompressible state. And as the confining pressure increases, the strength and the modulus of the soil increases. That is, if you have a soil deposit at a larger depth, the same soil at the same relative density might exhibit a stiffer response and a higher strength because of more confining pressure, and that we see from our triaxial compression test. This is the same soil placed at the same relative density, but tested at different confining pressures of 345, 690, 1035 and 1725, and you see that as the confining pressure is increasing, the strength is increasing, and it's not only the strength but also the slope of this initial slope of these stress strain curves, they are increasing. So that means that at higher confining pressure we will have a higher modulus, and this is the corresponding volume change behavior. At larger confinement, you will have more volumetric compression, because the soil will have so much strength that you have to mobilize so much of shear stress before the soil starts failing or undergoing plastic deformations. So, you will see that at a larger confining pressure, the soil will compress for longer duration or longer up to larger shear strains, and then only they will start expanding. And this is at 345, and then this is at 690, and then 1035, and then 1725. And these are all the responses that we get with the different dilation angles. So, after plastic failure, if this curve is flat, that means that it is a dilation angle of 0, and with a higher dilation angle we will see higher slope. Then what distinguishes between what is the factor that distinguishes between the dense sand behavior and the loose sand behavior? That is the critical void ratio. So, initially if we place the soil at a very large void ratio and then start shearing, it will go on compressing up to some critical state. When your void ratio reaches a critical value ECR, then if you perform the same test by placing the soil at a very low void ratio. Initially there might be some compression because of rearrangement of particles, then because of dilation soil will expand, and then at a large shear strain it might also reach the same constant void ratio that we call as the critical void ratio. So, the critical void ratio is the void ratio at which the soil does not undergo any volume changes under shear straining. So, if it is a loose sand it will compress, and if it is dense sand it will expand in volume, and at a very large shear strain the soil will reach a critical state when it will deform or it will undergo shear strains without any corresponding volume changes, and that void ratio is called as ECR or critical void ratio. And this critical void ratio is not a constant, is going to change with normal pressure. So, at a lower normal pressure sigma n is at a very low sigma n, ECR is very large, whereas at very high confining pressure your ECR could be small. And if your initial void ratio is less than ECR, the soil will behave like a dense sand that is expanding in volume, and if your initial void ratio is more than that of ECR, the soil will behave like a loose sand. And so, at a very low normal pressure, even a soil with a very high initial void ratio might behave like a dense sand, because this void ratio is less than the ECR. Okay. So, that explains why some the so called loose sands they expand in volume at some confining pressures. So, at very high confining pressures even dense sands may behave like loose sands, that is undergoing constant increase in the shear stress with the shear strain and then volumetric compression. And is actually this we need to know their behavior so that we can choose an appropriate constitutive model. So, if it is a loose sand, it is enough if you have some elastic model, because anyway it is going to undergo volumetric compression, it is not going to undergo any expansion. But if you want to simulate the dense sand behavior, you need some elastic plastic model so that we can represent the dilation, the shear induced volume expansion. And so, these linear elastic constitutive equations we have seen earlier, these are the generalized Hooke's relations relating the different strain components to the stress components. The three normal strains epsilon xx, epsilon yy and epsilon zz are related to the normal stresses sigma x, sigma y and sigma z, and the Poisson's ratio mu. Okay. And the shear strains gamma xy is tau by g, gamma yz is tau yz by g, and so on. And the inverse relation that expresses the stresses in terms of strains is through this. This is our generalized three-dimensional stress state, where we have three normal stresses sigma xx, sigma yy and sigma zz, and then three shear stresses tau xy, tau yz and tau zx. And in general we write stress as some constitutive matrix D multiplied by epsilon, and since our finite element analysis is based on displacement, we are using a displacement approach where our displacements are the basic unknowns. From the displacements we get the strains, and from the strains we can get the stresses through the constitutive equations. And the relation between the strains and displacement is through our compatibility equations, that is epsilon xx is dou u by dou x and so on. Okay. And let us look at the stress tensor once again. A 3-dimensional stress tensor is written like this: sigma xx, sigma yy, sigma zz. These three are the normal stresses. Sigma xy, sigma xz, sigma yz are the shear stresses, and we have seen this diagram earlier, and the convention is the first index sigma x is the stress that is acting normal to a plane perpendicular to that axis, and then sigma xx means it is acting on a plane normal to the on a plane normal to the x axis and in the direction of x, and sigma xy is the stress that is acting on a plane normal to x but in the direction of y, and sigma xz. And because of the equilibrium considerations, sigma yx and sigma xy should be the same. So, we write the equations like this, and this is the generalized 3-dimensional stress state, and these stresses are coordinate dependent. So, if I change the coordinate system, the stress magnitudes might change. So, that is why we call it as a stress tensor. It is not a stress matrix, but it is a stress tensor, because the tensor quantity depends on the coordinates. If you rotate the coordinate system, your stresses also will change. And corresponding to the 3 directions, we will have 3 principal stresses acting on 3 principal planes. So, actually that we have to do some analysis to get the principal stresses and their and the planes on which they are acting, and the shear stresses are absent on the principal planes. Let us look at our 2-dimensional stress state for simplicity. Let us consider our stresses like this. And our convention for the stresses is tensile normal stresses are taken as positive, that is the elasticity convention. So, our sigma yy, sigma xx are both tensile. So, we take them as positive, and then any shear stress that is causing clockwise moment about a point in the interior, it is called as a positive shear stress. So, the tau xy acting on the horizontal plane is taken as positive, whereas the tau xy acting on the vertical plane is taken as negative, because that is producing anti-clockwise moment. So, how we can determine the principal stresses is very simple, like we can draw the Mohr circle, and we can also determine them as the roots of this the determinant equation like this. Say if sigma are the roots, we can set up the equation for determining the roots like this: sigma xx minus sigma, sigma xy, sigma xy, sigma yy minus sigma. The determinant should be 0. Let me just get back to my laser. Okay. So, this is our governing equation for getting our principal stresses. So, if you expand this, this is sigma xx minus sigma multiplied by sigma yy minus sigma minus sigma xy square is 0. And so, after simplifying your sigma 1 and sigma 3, the sigma 1 is the major principal stress, and sigma 3 is the minor principal stress, that is equal to sigma, sorry, I think it should be plus or minus. Okay. So, here our major and minor principal stresses can be determined as the roots of this equation, and this is our familiar equation. It's actually a quadratic equation, and we know how to get the roots, and we can draw the Mohr circle and get our principal stresses and then the directions of these principal planes. So, our sigma xy, sorry, sigma yy and sigma xx, let us say our sigma yy is more than the sigma xx, and then the tau xy acting on the horizontal plane, where sigma yy is the normal stress, is positive. So, this is positive, and the tau xy is acting on the vertical plane is taken as negative. So, we get the 2 points, and we can connect both of them with a straight line, and this is your center point or the mean normal stress, sigma xx plus sigma yy by 2. And if you draw a circle, we know that we get your major principal stress here, and sigma 3 is the minor principal stress, and sigma 1 is basically sigma xx plus sigma yy by 2 plus the radius, and sigma 3 is the mean stress minus the radius, and we get the same equation as shown here. So, this is actually, it is a very convenient method, like we can draw the Mohr circle and then determine our major and minor principal stresses. So, now let us see the 3-dimensional stress state and how to determine the 3 principal stresses. So, we can set up the same equation. The determinant of this matrix is 0, sigma xx minus sigma, sigma yy minus sigma, sigma zz minus sigma. The determinant is 0, and this procedure is the same as how we find the eigenvalues in the dynamics. So, the sigma are the 3 roots of the above equation that give sigma 1, sigma 2 and sigma 3, and we can expand and write a characteristic equation like this. It is a cubic equation, sigma cube minus I1 sigma square plus I2 sigma times sigma minus I3 sigma is 0, and here I1 sigma is the sum total of the 3 normal stresses, sigma II is actually in the, if you have an index notation with a repeated index, means it is a summation on the I varying from 1 to 3, and in 3 dimensions I varies from 1 to 3, and in 2 dimensions it varies from 1 to 2. Sigma II basically means sigma xx plus sigma yy plus sigma zz, and I2 sigma is actually its determinant of the sub matrices, the sum total, because we have 3 coordinates. So, we have 3 determinants like this. Then I3 sigma is the determinant of our stress tensor, and if you get these 3 quantities I1 sigma, I2 sigma and I3 sigma, we can now write our invariance of the stress tensor J1 is sigma II, that is sigma xx plus sigma yy plus sigma zz, and that is also equal to the sum total of the three principal stresses, sigma 1 plus sigma 2 plus sigma 3, and the second invariant of the stress tensor J2 is 1/2 of I1 sigma square minus 2 times I2 sigma, where I2 sigma is the is the sum total of the 3 submatrices, determinants of the 3 submatrices, and that we can also write as 1/2 the product of sigma ij and sigma ij, the term by term product, like this: 1/2 of sigma xx square plus sigma yy square plus sigma zz square plus 2 times sigma xy square, because we have 2 sigma xy's. Similarly, 2 sigma yz and 2 sigma xz's. Okay, xz or zx both are the same. And the third invariant of the stress tensor J3 is 1/3 of I1 sigma cube minus 3 times I1 sigma, I2 sigma plus 3 times I3 sigma. This is these are the invariants of the stress tensor, and this stress tensor, if you apply this on a soil, would it cause any failure or not? See, that depends on the predominance of the shear, because our the soil will fail only under shear stress, and if you apply compressive stresses, pure compression, the soil will have infinite strength. In fact, it is so high that we do not really bother defining the compressive strength of the soil. And similarly, we do not define any tensile strength because we know that it is negligible, but it has some finite shear strength. So, we talk in terms of the shear strength of the soil. So, as the failure of the soil is due to shear stresses, it is interesting to split our stress tensor into 2 parts. One is a deviatoric part and the other is the spherical stress tensor. Spherical stress tensor, that is also called as the hydrostatic pressure state, and the hydrostatic pressure state is when all the 3 normal pressures are the same. So, sigma we can write as P plus S. P is the hydrostatic pressure, S is the deviatoric stress tensor, and the P is 1/3 sigma kk delta ij. Sigma kk is basically it's a repeated index. So, it is sigma xx plus sigma yy plus sigma zz, or you can call it as a mean normal stress. Delta ij is the Kronecker delta, and it is 1 when I is equal to j and 0 when I is not equal to j. In fact, delta ij is our diagonal matrix with a unit value, and our P is basically a stress tensor with the mean normal stress along the diagonal, and then our S is the deviatoric stress tensor, and our P, the spherical stress tensor, is the mean normal stress, and we have along the diagonal we have the same the quantities sigma xx plus sigma yy plus sigma zz by 3, 0 0 0 everywhere, all the off diagonal terms are 0, and the deviatoric stress tensor S is Sxx, Sxy, Xxz and so on, and that is equal to total stress tensor minus the P, and so this is sigma xx minus j1 by 3 sigma xy sigma xz, and then sigma yy minus j1 by 3, where j1 is the first invariant of the stress tensor, that is sigma xx plus sigma yy plus sigma zz. Okay. Same thing with the third quantity sigma zz minus j1 by 3, and we can similar to the invariance for the total stress tensor, we can write the invariance for the deviatoric stress tensor. J1d is Sxx plus Syy plus Szz, the sum total of the 3 normal deviatoric stresses. And if you look at this, these are the 3 normal deviatoric stresses. So, sigma xx minus j1 by 3, sigma yy minus j1 by 3, sigma zz minus j1 by 3. So, if you add them up, you get sigma xx plus sigma yy plus sigma zz minus 3 times j1 by 3, that is j1, and the j1 is nothing but sigma xx plus sigma yy plus sigma zz. So, the j1d is 0, and the subscript d indicates corresponding to the deviator stress tensor. J1 is the invariant for the stress tensor, the total stress tensor, whereas j1d is the invariant for the deviatoric stress tensor, and j2d is the second invariant of the deviatoric stress tensor, that is 1/2 of Sij multiplied by Sij, and then the j3d is the third invariant of the stress tensor, that is equal to the determinant of the deviatoric stress tensor. In fact, if you look at these equations, the j2d is basically I1 sigma is 0 for the deviatoric stress tensor, and you are left with only I2 sigma, because the 2 gets cancelled out, and I2 sigma is this quantity. Okay. And then the J3 I1 sigma is 0 for the deviatoric stress tensor. So, you are left with only I3 sigma. I3 sigma is the determinant, and for the deviatoric stress tensor, this is just the determinant of the deviatoric stress tensor. Let us look at a small numerical example. Let us take a stress state where our sigma x and sigma y are the same, normal stresses are the same in both x and y directions, and then sigma zz is 250, and then we have some normal stresses, and the mean normal stress, that is 1/3 of sigma kk, that is 100 plus 100 plus 250, that is 450 by 3, that is 150. And actually, even before you calculate, you can also say that the sum total of the 3 principal stresses, sigma 1 plus sigma 2 plus sigma 3, is equal to 450, because that is an invariant, and that is not going to change. So, once you get your mean normal stress as 150, the spherical stress tensor P is 150, 150, 150, and the deviatoric stress tensor is sigma minus P, that is minus 50, 25, 30, 25, minus 50, 45, 30, 45 and 100. So, this is your deviatoric stress tensor, and this is your spherical stress tensor, and the spherical stress tensor is representing hydrostatic compression, and if you apply compressive stress, the soil will never fail, and your failure will not happen because of your spherical stress tensor. The failure will happen only because of the deviatoric stresses. Okay. So, our I1 sigma is 450, that the sum total of the 3 normal stresses. I2 sigma is 56,450, and then I3 sigma is 2,118,750, and we can solve our cubic equation to get our 3 principal stresses. So, most of the calculators have the facility to solve a cubic equation, and you can easily set up this matrix and then find the roots and then the determinant and all the quantities that you require for doing these computations. So, if you do that, sigma 1 is 269.98, sigma 2 is this, and sigma 3 is this. sigma 1 is our major principal stress, sigma 2 is the minor principal stress, sigma 3 sigma 2 is the intermediate principal stress, and sigma 3 is our minor principal stress. Okay. And J1 is the sum total of the 3 diagonal terms are sigma 1, sigma 2 and sigma 3, that is 450, and J2 is 1/2 of I1 sigma square minus 2 times I2 sigma, that is 44,800, and J3 is 1/3 of I1 sigma square minus 3 times I1 sigma times I2 sigma plus 3 times I3 sigma. I3 sigma is the determinant of that stress matrix or the stress tensor, sorry, and that's this much. And similarly, we can take the deviatoric stress tensor and determine the invariance. J1D, that's the Sxx plus Syy plus Szz, that's equal to 0. J2D is 11,050 and J3D is 401,250. Actually J2D is just simply 1/2 of the term by term product of the deviatoric stress tensor terms, and the answers are given, so you can work out on your own because all the equations are given and then the stress tensors are given. This is the S, okay, and J2D is 1/2 of 50 square plus 50 square plus 100 square plus 2 times 25 square, 2 times 30 square plus 2 times 45 square. Okay. And if you do that correctly, you will get this, and then the J3D is the determinant of this matrix. So, around the time of when Hooke proposed his generalized stress strain equations, there was another mathematician by name Lamé. He proposed a similar equation, like similar to what we have seen just now, the stress tensor being equal to the sum of the spherical stress tensor and then the deviatoric stress tensor. He has given an equation in terms of lambda and mu, which are called as Lamé's parameters, and the first term here represents our spherical stress tensor. Lambda is some parameter that relates to the bulk modulus, and epsilon kk is our volumetric strain, epsilon xx plus epsilon yy plus epsilon zz, and our epsilon ij is we will see that is that's we call as the engineering shear strain. Lambda and mu are called as Lamé's constants, and our epsilon kk is epsilon xx plus epsilon yy plus epsilon zz, and epsilon ij is the scientific definition of shear strain, that is 1/2 of dou u by dou x plus dou uj by dou xi, or basically it is dou u by dou x and dou you see this index I here and j there, dou ui by dou xj plus dou uj by dou xi, that is the cross differentiation, like dou u by dou y plus dou v by dou x, okay. And this is half. The average of the change in the right angle is called as the shear strain in the scientific definition, and the engineering definition is the change in the right angle because of some distortion, okay. And our lambda and mu are given like this. Lambda is nu e by 1 plus nu times 1 minus 2 nu, and mu is our shear modulus, e by 2 times 1 plus nu, and this lambda is nothing but our constrained modulus that we derived long back in one of the classes. The constrained modulus or the odometer modulus, and if we substitute this lambda and mu in this equation, we can get back our relation between the stresses and strains in terms of that 6 by 6 matrix. We will get back the same stress strain equation. Okay. So, this is what we have done when we decompose the total stress tensor into deviatoric part and then the spherical part. And do not confuse the total stress tensor here with the total stresses that we have in the soil mechanics, because here the total stress tensor is the sum total of the spherical stress tensor plus the deviatoric stress tensor. Okay. Whereas in soil mechanics, the total stress is effective stress plus the pore pressure, and your pore pressure is similar to your spherical stress tensor, and then the effective stresses could be similar to your deviator stress tensor. Okay. So, I think this may be my last slide. Okay. So, thank you very much, and if you have any questions, please write to me at this address, and then I will respond back to you. So, thank you very much. We will meet in the next class.